Welcome back, everyone, to today's Explainer. We're getting into something today that acts as the literal beating heart of modern AI retrieval. I'm talking about embedding models. If you've interacted with a smart assistant or a RAG system, Retrieval Augmented Generation, you are already relying on these models. So let's uncover the secret sauce that makes them work, shall we?
Okay, let's dive into this. At the absolute most fundamental level, we really have to ask ourselves, how does a machine, which, let's be honest, is basically just a giant calculator, how does it actually understand human intent? When you type a question into a search bar, how does the computer grasp what you genuinely mean, rather than just blindly matching the letters you typed? That massive gap between human language and machine comprehension is exactly what we are solving today.
Here's our quick roadmap for today. We'll start with meaning coordinates in space, look at the math behind search, do a step-by-step walkthrough of RAG, cover types of embeddings, dive into building for production, and finally look at exactly what happens when embeddings fail. All right, part 1, meaning coordinates in space.
For decades, computers relied entirely on old-school keyword matching. But just take a look at these two phrases for a second: fast car and quick vehicle. Any human reading that instantly knows they mean the exact same thing, right? But to an old-school keyword search, they share literally zero overlapping letters, so the computer just assumes they have absolutely nothing in common. That is a massive hurdle if you actually want an AI to be helpful.
To solve that problem, we use an embedding. Now, what's really interesting about this slide is how it fundamentally shifts the focus to semantics. An embedding takes our text and converts it into a dense vector representation of meaning. It essentially turns a concept into a list of numbers, like 0.21, negative 0.87, 0.44. And the real magic here is that in this numerical format, distance equals semantic similarity. Close numbers mean similar meaning. The absolute best mental model for this is to think of them as meaning coordinates in space. Just imagine this massive, multi-dimensional map. Every single word, every sentence, every document you feed the AI gets assigned its own specific GPS coordinate on this map. Ideas that are totally unrelated, they end up on totally opposite sides of the universe. But concepts that are similar, like our fast car and quick vehicle, they're plotted right next door to each other. Searching just becomes as simple as finding the nearest points on the map. Moving on to part 2, the math behind semantic search. Now, obviously, there isn't an actual physical map inside your computer. It's all just math. So how does the AI actually calculate how close two concepts are? Well, it uses something called cosine similarity. Now, don't let the formula intimidate you. The intuition here is actually beautifully simple. Think of A and B as two different embeddings, right? Two different ideas. This equation just measures the angle between those two vectors in space. If the angle is super narrow, the resulting cosine value is high, which mathematically proves that the two ideas are incredibly similar. A higher value simply means a much closer match in meaning. Let's look at part 3, step-by-step in RAG.
So how do we take this beautiful math and actually build a real-world application? In a Retrieval Augmented Generation, or RAG system, it all boils down to 3 core steps. First up, offline document embedding. You take all your company's data, chunk it up into smaller pieces, embed those pieces into vectors, and stash them in a vector database. Then, step 2. When a user comes along and asks a question, you take their query and run it through that exact same embedding model to get a query vector. Finally, step 3, similarity search. The system literally just asks the database, hey, find me the top 5 vectors sitting closest to this query's coordinates. And boom, you get a semantic match, entirely bypassing the limits of simple keyword search.
Next step, part 4, types of embedding models. To build this pipeline, you really have to choose the right tool for the job. Not all embedding models are created equal, and knowing the difference is key. We generally look at 3 main types. Dense embeddings, that's what we've been talking about so far. They're powered by neural nets, capture really deep semantics, and they are the gold standard for modern RAG. Then you have sparse embeddings, things like BM25. These are your traditional keyword-based exact term matches. But the real magic happens with hybrid embeddings. This setup combines the deep contextual meaning of dense vectors with the precise exact matching of sparse vectors. It literally gives you the absolute best of both worlds. And this brilliantly illustrates why getting that choice right is so transformative for performance. Just look at the massive upgrade across the board here. Without a solid semantic embedding, synonyms are completely missed, your context is incredibly weak, and both your overall recall and accuracy are just plain poor. But with it, You capture all those subtleties, the context becomes super strong, and your system starts to feel genuinely intelligent because it actually understands the user's intent. Which brings us to part 5, building for production. Getting the theory is great, but shifting into actual production, that requires some tough choices. Building scalable intelligent systems means you are constantly forcing engineers to balance competing priorities. The first major design trade-off is balancing raw speed against semantic accuracy. A smaller embedding model is going to give you lightning-fast latency, which is great for user experience, but it might miss some subtle nuances. A large model, on the other hand, gives you incredibly high-quality, rich semantics, but it's going to be a lot slower and way more computationally expensive. You really have to tune this based on what your specific application demands. Next, you've got to balance recall versus precision, which usually comes down to dimensionality. Just think of dimensionality as the number of coordinates in your space. A vector with, say, 384 dimensions is lightweight and super fast. It gives you broad embeddings with high recall, meaning it casts a really wide net. But if you want sharp, precise embeddings that pretty much never make a mistake, you might need to bump that up to 768 or even 1536 dimensions to map out a much richer semantic landscape. Now, to handle all that data at scale, your infrastructure has to be absolutely rock solid. You simply can't compute everything on the fly. You've got to pre-compute and index your document vectors using specialized databases like Pinecone or libraries like Face. You absolutely need to cache frequent queries, and most importantly, if you want to search through millions of vectors instantly, you rely on approximate nearest neighbor algorithms. Tech like HNSW or IVF indexing will sacrifice just a tiny fraction of perfect accuracy so they can deliver search results in literal milliseconds. Okay, once your basics are scaled up, you can start applying some really cool advanced optimization techniques. You implement hybrid retrieval. You start using query expansion, meaning if a user types something like DB slow, your system actually expands it out to database latency performance issues before it even tries to embed it. But I'll tell you, the real cheat code here is using domain-specific embeddings. If you are building an AI for a hospital, use a medical embedding model. If it's for trading, use a finance model. Analyzing system infrastructure, grab a model trained specifically on database logs. Throw in a feedback loop to track bad retrievals and fine-tune your model, and your system becomes remarkably powerful. Finally, part 6, when embeddings fail. So what happens when things actually go wrong? Because let's be real, they do. And when they do, it creates this massive domino effect. Here are your critical failure points. First, if a user inputs a terribly ambiguous query, the vector just ends up completely lost in space. If you use a general model for highly technical data, a domain mismatch, the coordinates are going to be horribly clustered. If you chunk your documents poorly, essentially mixing totally different ideas into one single vector, the meaning gets incredibly muddy. And if you skip a re-ranking step later in the pipeline, you might just feed the AI completely irrelevant garbage. Look, if retrieval fails here at the embedding stage, the entire downstream process collapses. The large language model has absolutely no good context to read, and boom, it hallucinates. So the crucial point is really this: unbreakable relationship. The quality of your embedding perfectly dictates the quality of your retrieval, and the quality of your retrieval completely determines the accuracy of your RAG system. Your entire AI application depends, fundamentally, on this single layer mapping meaning correctly. No pressure, right? Which really leaves us with a fascinating paradox to ponder as we wrap up today. We've seen how brilliantly these dense vectors translate human intent into mathematical space. But language isn't just raw data, is it? It's emotion, it's sarcasm, it's cultural context, and it's unspoken implication. If an AI relies purely on a mathematical map of meaning coordinates, how will it ever truly navigate the beautifully irrational nuances of real human conversation? It's a limitation that pushes the boundaries of exactly where AI goes next, and I really hope it leaves you eager to explore further. Thank you so much for joining me for this explainer. Keep exploring, and I'll catch you next time.